So before I start, I'd like to thank Mary Ann and the Krell Institute for asking me to give this talk. This is one of my favorite conferences to come to every year. I've been coming almost every year since I entered the program, the CSGF program in 1999. First as a CSGF fellow. Then when I graduated, I was lucky enough to come back and give a House Scholar talk. So that was kind of one of those years in between. And then when I was at Sandia, I continued to come, and now Oak Ridge asks me to come every year, and it's a highlight of my year, honestly. So I've been thinking about this talk for quite some time, since Mary Ann asked me to give it. And really, I'm going to pose it as an optimization problem. The question is, how can I give the best talk about, and I quote from Mary Ann's original invitation, science, reflections on the program, career trajectories, and impacts the program has had or continues to have on your professional life. Now, if we assume no constraints to this problem, I still don't know what the optimal solution is. But then we have some additional constraints. The first of which is the audience. You guys are some of the most intimidating people I know. And Jay Bardhan put it very succinctly yesterday that you guys give some of the best talks at conferences that I've ever been to. So you guys are pretty intimidating for me. Second constraint is it's 9 o'clock in the morning, and I realize some of you are from the West Coast, so it's really 6 o'clock for you. Now, you've had a couple of days to wake up, but it's still pretty early for me. I really only have an hour, not even a full hour, probably closer to 45 minutes to reflect on this great program and the impact it's had on my life. So I'm going to have to cram a whole lot of things in very quickly. And I definitely haven't, when I wrote this, I said I probably haven't had enough sleep. I can say with pretty good certainty that I definitely haven't had enough sleep tonight, or last night. So we'll see what we can do with that. So here's my, I forgot to say, this is a global optimization problem for those of you in optimization. There are many local minima. I'm not sure I can find the global minima to this problem. But here's my suboptimal solution. I'm going to give, since this is a keynote and you guys cover such a wide breadth of expertise, I'm going to give something of a non-technical talk this morning. I'm going to talk about my research, hopefully in a very high-level way. I have a tendency to dive a little bit deep at times, so I'll try to not do that. I'm going to cover a lot of topics that I've done in my past, but I'm going to skip a lot of the details. So forgive me if something doesn't sound, if it's your area and something doesn't sound quite right. I'm probably saying something to give a high-level look at the problem rather than the actual details. But what I hope that you'll gain at the end of this talk is I hope you'll find something of interest in the experiences that I've had as a result of this great program. So the general conference theme this year has been 20 years of building a community of leaders. So I thought I would look at the evolution of high-performance computing in the last 20 years. And I'm not going to go quite clear back to 1991, but I'll start with 1993, and I'm going to sample a few different points through the last 20 years and talk about my experience in computing as well as what I've kind of observed in HPC in that time. So 1993 is the first year I'm going to talk about. And for each of these sample points, I'm going to pick 3 points on this curve. And this curve is really the years, and I'm going to look at the peak performance of HPC resources for that point in time. And back in 1993, the number one computer on the top 500 list, the very first list, I might add, which is one of the reasons I chose 1993, was a Landau machine that had 1,000 cores. It went a whopping 131 gigaflops. Our cell phones probably go about that speed now, don't they? What I also find interesting is, at that point in time, the reason I chose 1993 is that was the year I graduated from high school, and I went into the computationally intensive field of civil engineering at a land-grant institution called Kansas State. So I was definitely in the HPC world at that point. Not at all. My computing experience at that point in time was on my desktop computer, approximately a 486. I'm thinking it was a 20 megahertz processor. So not real sophisticated. Actually, for the time period, it probably was pretty sophisticated for the desktop computer. It was probably running Windows 3.1, for those of you that weren't born yet. At home, we were actually relatively computer savvy. We had internet dial-up through AOL, so we could get on the internet. And I generally used it to do word processing, write those high school and college papers, as well as play a few computer games like Myst. So that was my auspicious beginnings in computational science. Let's skip forward 3 years, which is where I got my first exposure to the Department of Energy. In 1996, as a junior in college, I had actually the very, very good joy to go to Pacific Northwest under a program that's currently probably known as the SULI program. At the time, it was known as the SERS, the Science and Engineering Research Semester. And that semester, I got my first exposure to computational science, where I was seated in the computational chemistry group. Now, having had some undergraduate students since then, that I've supervised now, I probably didn't do anything for them, but they did a lot for me. They taught me C. That was the first real exposure to programming outside of college. And in college, at that point, I'd had a half a semester of Fortran. So I got my first programming experience, real programming experience. But the most important point of that experience was that I decided to go to graduate school that semester. I decided I liked computing, even though I probably wasn't doing very much that was useful for them. And I made the decision while I was away from college that I wanted to apply to graduate school that semester, well, the following fall semester of my senior year. The second good thing that happened to me in 1996 is I talked to my college professors and realized how important mentoring was to me. One of my college professors at the time had a graduate school colleague that was at Carnegie Mellon, and I talked to her about where I was applying to graduate school, which was MIT, Illinois, Texas, Kansas State, all good civil engineering schools. She said, you might want to consider Carnegie Mellon. I have a colleague there. I said, okay, let me give it a shot. I'll put an application in. Lo and behold, I got accepted and chose to go to Carnegie Mellon over MIT simply because of the size of the university and the size of the city. Pittsburgh versus Boston to a small-town Kansas girl was a big difference. The other thing I did that year was I started a bachelor's thesis on numerical modeling using neural networks of the fate and transport of pesticides through turf grass. So still a very civil engineering type topic. But you can see that I was moving towards computational science. I should also point out that at that point in time, we'd made vast improvements in our processors, and I was using now a desktop computer that had 150 megahertz Pentium processor. It was cutting edge at that point in time. The top computer in the world now had twice as many cores and 3 times as many gigaflops available. So now, let's see what happens. We fast forward to 1999. Things haven't changed much. I went to Carnegie Mellon. I graduated with a master's degree in civil engineering from Carnegie Mellon. I did an experimental and a computational thesis. So I was still starting to move towards computation, but I was still in the laboratory doing some measurements and trying to do some predictive simulation based on those measurements. Now, the difference between my computational thesis in this case was using a commercial finite element package called Abacus. So I still hadn't moved into numerical modeling or numerical methods development at this point. I was just a user of some software. But the key point here was that I was awarded the CSGF fellowship. And I think come the next slide, you'll see a big difference in my computing experience. So I was still using a desktop computer. We're starting to enter the era of more massively parallel simulations where we have ASCII-Red come online sometime in this time period. Oh, and I should say we also, the DOE broke the teraflop barrier sometime between 96 and 99. When I put these machines up, they are not necessarily when they were introduced. They're just what they were, the best machines at the time. So then we go to 2004. We have online an IBM machine that has 32,000 cores, so a factor of, roughly 4 increase in the number of processors, a significant increase in the number of flops that are available to us. But that was the year I graduated with my PhD in computational science. So I'm no longer now considering myself a civil engineer. I'm considering myself a computational scientist where I'm focusing more on methods development. The real improvement is the machines that I now have access to. I'm no longer working on my desktop computer. I'm using a machine at the Pittsburgh Supercomputing Center called LeMu, which when it was brought online in about the 2001 era was actually the fastest academic machine available, located there in Pittsburgh. And it had a peak performance of about 3 teraflops. So let's dive in and see a little bit about the research that I was interested in at that point in time. And we're going to try and then draw some conclusions We're going to look at a few vignettes of the research that I've done throughout the last 7 to 10 years and how they're more computational than where I started. Okay. So the problem that I was solving at this point in time was motivated by hemodynamic devices. For those of you that aren't familiar, hemodynamic devices are not artificial hearts. They're artificial heart assist devices. So as an engineer, this problem piqued my interest. So we had some colleagues or some collaborators at the University of Pittsburgh Medical Center that were doing numerical modeling of their prototype designs. And what they were looking for was a design that minimized the shear stress present in these artificial heart design or artificial heart assist devices. So they did macroscopic CFD modeling and design optimization. But they did this in a very crude way. They essentially sampled the parameter space at their whim based on their physical intuition. They didn't do any kind of numerical optimization yet at that point. And their simulations were really based on macroscopic homogeneous flow models, so simple Navier-Stokes. Now, what we noticed as computational scientists is that that particular model doesn't necessarily tell you much about the flow regime. The question really is, can you sustain those high shear regions if there aren't any red blood cells? So if you're familiar with red blood cells, they can't sustain high shear stress. They rip apart, your patient dies. Not really the outcome that you're looking for. So their first design up on the top there had these areas with these dark blue areas. Those are areas of high shear. And their concern was if red blood cells were in there, that the patient could eventually die because they're killing their blood as they're trying to help the patient. So their goal was to minimize the shear. The question that we wanted to ask was, what does the flow actually look like? If the red blood cells aren't near that bearing right there, you could actually use that design just fine, and perhaps it's more efficient than these other designs that were less efficient but might not kill, from their point of view, might not kill the patient. The problem was these macroscopic models they were using fail in these regions. The length scales are too small. They couldn't say anything specific about the red blood cells. So it was really the first multi-scale problem that I started looking at. So the challenges that you have when you do this kind of modeling is that the microstructural blood flow modeling, you're trying to model actually the individual red blood cells. You have large relative motion between the cells. These cells are squeezing past one another. They change where they're located. They change their nearest neighbors. You can't do a very simple sphere-like model. It just doesn't work. The other problem that you have is that the cellular membranes, as they're squeezing through the capillaries and through these artificial heart assist devices, is quite large. They have large deformations. So the shape of the red blood cell is changing. So at that point in time, what was generally done was you would discretize these red blood cells, and then you would discretize the plasma. You generally ignored everything else in the blood at that point. Well, the challenge with doing that is you're starting to look at your mesh motion. As these flows evolve, you've moved your mesh so far that you have to constantly remesh. And in 2 dimensions, this really wasn't a problem, but when they started to think about 3 dimensions, they decided that they would very quickly encounter a remeshing problem. So I decided to take a different approach. Instead, we're going to look at it from an Eulerian point of view. And so for those of you that are not familiar with an Eulerian versus a Lagrangian point of view, a Lagrangian point of view, you can essentially say I'm sitting on a mesh point, and I'm going to move along with that mesh point. So if that mesh point gets moved by the velocity field to over here, I'm moving with it. We decided to do something different, and we were going to use an Eulerian point of view, where you're sitting on the bottom of the stream, the world is moving past you, and you're observing what's moving past you at the same time. The advantage for doing this at this point in time was that you have none of these remeshing issues that you had with Lagrangian methods. So I'm going to try not to dive very deep, but I do want to show you the magnitude of the problem that we were interested in solving. So if you just solve for the fluid flow, so you're only solving the fluid equations, ignoring the red blood cell membrane problem that we've talked about, this membrane deformation, what equations would you solve? You'd naturally solve the Navier-Stokes equation. So for a viscous, immiscible, incompressible fluids, you would solve a balance of mass, which is the top equation, just a pure hyperbolic convection equation, as well as the Navier-Stokes equation. I will say that the balance of mass up there doesn't look like the balance of mass that you might want to normally use, but we're taking a phase field approximation, and I won't go into those details. But what you do know is that the Navier-Stokes equation is nonlinear. You have this nonlinear convective term, generally considered not real easy to solve, especially at this point in time. Then we're going to make it worse. We're going to add a membrane at that interface. So we have to add an additional stress term that accounts for that membrane stress there. When we add that stress, some computational geometry says that we need to keep track of the rotations of the membrane. We also need to keep track of the strain of the membrane. It looks not great, but then when I tell you that the membrane rotations and the membrane strains are actually tensor quantities, you start seeing that the degrees of freedom of your problem are increasing quite quickly. When I add to the fact that the membranes for red blood cells, if you look at the actual physical parameters, are actually quite stiff, this becomes a very difficult computational problem. So we had to start making some simplifying assumptions, as all applied mathematicians do. The first thing we're going to do is we're going to take out the nonlinearity in the Navier-Stokes equation. We're going to lag that convective term in the nonlinear portion of the Navier-Stokes, simply for numerical convenience. We're also going to decouple the first equation, what I call the phase field equation or the balance of mass equation. We're also going to decouple the membrane rotations. We found that that didn't significantly affect the quality of our results. However, we cannot lag the strain equation. We must fully couple the strain to the Navier-Stokes equation. So you still have a highly coupled large system of equations that you have to solve. So the algorithm that we came up to solve, like I just stated, was we're going to solve the phi equation, or the phase field equation, and the R equation. Now, those were hyperbolic problems, so we're going to use discontinuous Galerkin, which is going to bias quite a lot computationally. It gives you a nice block-sparse structure, so we can solve those equations very quickly. The real problem that we encountered was solving this coupled momentum and strain equation for the velocities and the strains in that membrane. We're going to use a standard finite element Galerkin approximation for the velocities and a discontinuous Galerkin approximation for the strains. And this was, when I was solving this problem, this was my first foray into computational high-performance computing, and we employed at the time the PETSI library of linear solvers and preconditioners. This was all fully parallel. And so I showed you that beautiful picture at the very beginning that showed these red blood cells pushing past one another, et cetera. We didn't have the computational horses to solve that problem at that point in time. This was about the limitation of the problem that we could solve using this particular approach. So you can see that I have 3 blood cells per se, located in a computational domain. I'm using only 60 by 60 elements, and the degrees of freedom was approaching about 500,000 degrees of freedom. This particular problem we could solve only on about 32 cores on Lemieux at the time. But you can see the problem that we encountered was that the stiffness of the system made the iterations go up, even with preconditioning, and I'll talk about that in a second. So I call this my Mickey Mouse simulation. But you can see the blood cells interact, they move around from one another. Okay. We could also do it in 3 dimensions. You can see that the degrees of freedom go up significantly. So in the prior case, I was doing 60 by 60 elements. Now I'm doing 16 by 16 by 16 elements, so not very many elements. And I'm still well over 500,000 degrees of freedom very quickly. In this particular example, I'm not showing the membrane, but I'm showing that we can, the algorithm works. It drops to the bottom and puddles. So what were the things that we were thinking about at this point in time? Really, this was a novel at the time. Remember, take all of this in the context of when the simulations were done. Demonstration of an elastic membrane in Eulerian flow description, which really wasn't being done at that point. So we demonstrated that you could do an interface capturing type method rather than an interface tracking method to model these kind of problems. The advantages that we got from that was that this fixed mesh never required remeshing, unlike the Lagrangian methods that I talked about. We didn't explicitly track the interface, and very little change was required algorithmically to move to 3 dimensions. What were the challenges that, if I could go back and solve this again now with the machines that I have today, that we might overcome? Well, first, I'm not sure we would overcome this one. Despite a fully implicit time discretization, which I didn't talk about, the stiffness in the system as a result of that membrane, that elastic membrane that I introduced, really hampered the convergence of our linear solvers. So we did a lot of physics-based preconditioning, which is probably about the best you could do. At least I still, even today, haven't come up with any better ideas. it still really wasn't adequate. The number of iterations, Krylov iterations to solve this problem was quite large. And at the time, we were flop limited, especially in 3 dimensions, because we were using high order basis functions to represent that interface, to get a good representation of where the interface was. Well, hindsight's now 20/20, and if I could go back and work on this problem again, I might use a different method, might use fast multipole if I could. I'm not sure I can. But what I find interesting is that we had lots of small, dense local matrices and a globally block-sparse structure for our linear system. So this actually may be very attractive. This type of method may be very attractive for our future architectures that are coming online, where we want to do lots of small, dense, fast calculations locally. So that was my first experience with high-performance computing. When I graduated, I'd had the opportunity to work on one of the top academic machines at the time. I really changed my focus, as you could see, from being a traditional civil engineer, now moving into being a computational scientist who focuses on numerical methods and algorithms. And that was really as a result of my program of study that I took during the course of those 4 years while I was on the fellowship. But the important part that I really want to drive home to the new fellows is you'll notice that I did not have any expertise in high-performance computing when I started with the fellowship. I was still using my desktop computer. But as a result of this fellowship, a lack of a background in HPC does not prevent a future in high-performance computing. So we'll fast forward a few more years to 2007, where now we're really entering the era of massive, lots of concurrency in our architectures. We have the Livermore machines online at more than half a petaflop with 200,000 plus cores. We can start considering problems that require repeated function evaluations, optimization problems, inverse problems. We now have some resources available to solve some of these problems that really weren't tractable before. At this point in time, I was employed at Sandia in the Computer Science Research Institute there. So I started thinking, broadening my experience and thinking about some new types of problems that built on what I had learned as a PhD student, but also I was learning something new. So I started looking at inverse problems. And for those of you that aren't familiar, an inverse problem is one that consists of using the results of actual observations that you measure to infer values of some parameters of your system that characterize the system under investigation. And you can find these problems all over science. These are some of the ones that I've worked on in particular. You can look at water distribution systems, looking for an initial condition that you're interested in. So that's initial condition inversion. You can look at material property inversion. Maybe you don't know everything about some piece of ground or some image reconstruction with MRIs. You can do material property inversion. The one we're going to talk about today is the identification of airborne contaminants or initial condition inversion. So the motivating problem that I was working on at this point in time was contaminant transport. So in this particular problem, the idea was that if you have some kind of unknown contaminant release, be it accidental or be it intentional, and you have sensors throughout your city or throughout the region that is affected that are picking up contaminants in the air, can you figure out where that release is going on? So we were doing this work in late 2004 to 2006. So you have to think of the context of the time. We were doing a lot of Department of Homeland Security type. We were all thinking along Department of Homeland Security type problems. So if you have the airflow, so the velocity fields from some mesoscopic weather model, can you measure or can you figure out where that unknown source location was just from a few sparse discrete measurements? So the problem is to identify the source of this airborne contaminant from these sparse sensor measurements. And we made some very simplifying assumptions in the context of this work. First of which is that the contaminant is going to be transported by both convection and diffusion, and that we know the diffusion coefficient. You're not going to know this in real life. But to demonstrate these algorithms, we decided to do this. The second thing we assumed is that we knew the velocity field. We knew how the wind was blowing in the convection operator for the contaminant transport, and that it was static. If we don't know this, it becomes a velocity inversion problem, which is still an open research problem even today that some colleagues are working on. So when I first approached this problem, the first thought you might think is, well, these are really convection-dominated problems. Maybe I could take this naive approach, just follow those streamlines backwards and figure out where the contaminant started from. So I would just, in that sense, run backwards in time. Well, this problem is ill-posed, and it can be ill-posed for several reasons, but the reason in this particular case that it's ill-posed is that the solution is sensitive to changes in measurements. I'm not going to say any more about that. If you have questions, I'd be happy to talk about why that's the case later. So instead, we're going to formulate it a little bit different. We're going to formulate this as a real-time inversion problem. We're going to formulate this real-time inversion problem as a constrained optimization problem, where we're going to minimize some cost functional subject to some constraints, where those constraints can be equality constraints, but they could also be inequality constraints. And the decision variables, D in this case, are the inversion parameters. So in this particular case, for this particular application, we want to identify the source of this release from these sparse observations. So, good. We have measurements that I'm going to call U star that are sparse and discrete. So I have a delta function here that says at a particular point X, I've either got a measurement there or I don't have a measurement there. And I'm going to come up with a simulation result, and I'm going to minimize the difference between my simulation at those particular points to my measurements, subject to some constraints. Well, this particular optimization problem is also ill-posed because there are many solutions to this particular problem if I don't do something to change that. So we added some regularization. The good thing about this regularization is we could recover a unique solution at this point, but it only gives us the low-frequency components of this solution. It neglects the high-frequency components. So here's the problem we solved. We minimized that function I just showed you, subject to convection diffusion transport, given some local velocity field V and some diffusion coefficients K. Okay. So what were we thinking about at this point in time? For these algorithms that we were designing, we really required rapid response. If you're in a contaminant release, if something's actually happened, you need to be able to answer where that contaminant's at very quickly. Well, how might you do that? You might do it by using variable fidelity models, or using some kind of reduced order model, where you've reduced the complexity of your system while not throwing away the relevant physics of it. And if you were to use either of these models, I would probably do what I call a non-intrusive optimization approach, where I have an optimizer that sits outside of my simulation problem. Well, the advantage of this is if you already have a forward simulation code, you don't have to do anything. You just wrap an optimizer around it. The disadvantage is, in particular for this case, our design space was very large. We were interested in the initial condition at every discrete point in that domain. So it's incredibly expensive to sample that system and come up with an optimal solution. So instead, we did something a little different. Instead, we decided to do the fast solution of the optimality conditions, which I'll introduce in a second, via parallelism. So instead, we wrapped the optimizer together with the simulator. So we did what we call an intrusive approach. The advantage of this is it gives you better scalability for large design spaces. It's really extremely computationally efficient, as I'll talk about in a minute. The real disadvantage is to the graduate student or the postdoc at the time. It's expensive in development time. You spend a lot more time developing software with this approach. But if we're going to take this approach, what do? We write the KKT system. So for those of you that aren't familiar with optimizations, really, if you go back to your beginning calculus and think about finding the minimum, what are you looking for? You're looking for where your gradient of your function is 0. That's really all we're doing here with the optimality conditions. We take that system of equations that we had before, and we take the gradient of it, ask where it's 0. And the goal is we solve this system for U0. Well, what challenges were we going to encounter as we started to implement this? The size of the parameter set, U0 in this case, increases with increasing problem resolution. It's going to also require numerous repeated forward simulations, probably not as much as a non-intrusive simulation might, but we're still going to have to solve a forward problem a few times. And it's a boundary value problem in space-time. So the size of your forward simulation, if you're doing a high-fidelity simulation, is really going to govern the amount of time it takes to solve this particular problem. So how might we get around, or how might we solve some of these problems? Well, we're going to use an adjoint method. So I said it takes numerous forward solves. It's actually going to take numerous forward and adjoint solves. But the number of these solves, if you're smart about it, is independent of the number of parameters that you're looking for. We're going to use a reduced space method. We're going to use a matrix-free method. So that optimality system is very large. You know, if I go back here, you have a system that is, if you solve a big linear system, it's going to be the size of U, which is space-time, the size of U0, which is space, and the size of your Lagrangian parameter, which is the size of space-time. So if you did all of that together, you would have a very, very large system. So instead, we're going to take a reduced Hessian approach, which reduces the size of this system down to the cost of just 2 forward solves. And we're going to employ some very specialized preconditioning to be able to solve this problem computationally, in a computationally efficient way. So the results of what we did here is we developed a multi-grid preconditioner that solves this large scale problem that was previously intractable. So in this particular case, the results of this are actually in a supercomputing paper from 2005. So the results of this case is we had a grid that in space-time was 500 to the 4th, where the 4th dimension is time. That if you didn't employ any kind of preconditioner on 1,000 processors, you didn't get a solution. It just continued to iterate to the end of your wall clock time. Now, we didn't try checkpointing and restarting. We just decided that it was purely intractable. But if you employed some specialized algorithms that as applied mathematicians we work on, then you can actually reduce this to about 5 hours per iteration. So a previously intractable problem is now more tractable. But what's even more interesting is these multi-grid methods. It's proven from analysis that the number of iterations decreases as you increase your problem size. So that's a very nice property that we can bring to this problem. The other thing I should point out that the cost of this approach is approximately, you know, I'm hand waving here, 18 times that of a single high fidelity forward solve. If you did a non-intrusive approach, you're probably not going to be able to do it with just 18 forward solves. So it's really about 9 iterations, remembering that I have both a forward and an adjoint solve at every iteration. Okay. There's been some extensions to this work that I've helped with as well. Inversion under uncertainty has been an area of interest, as well as model reduction to take different approaches. I'm not going to talk about those. If you're interested in that work, please talk to me later. Okay. So that was kind of 2007. So what are the common threads that are pervading through the work that I've done so far? So I've clearly honed in that numerical methods for PDEs are something that I'm very interested in. You know, I'm using high-performance computing, but what I think is most important, especially coming from an engineering background, is I'm really application-driven. Now, I still work on what I call the toy problem side. I'm not really doing predictive science at this point. But you can see in the longer term, that's where this is kind of the early work that someone might use later on. So far, I've also now broadened from my PhD work that was purely in PDEs into optimization methods, while still leveraging some of that knowledge I gained as a PhD student. And then in late 2007, I decided to become an applied mathematician. Or at least people decided to classify me as applied mathematician when I moved to the computational math group at Oak Ridge. So despite having a civil engineering background, and despite having a computational science PhD, at Oak Ridge they consider me an applied mathematician. I'm not really sure how I've gotten that name yet, but that's okay. So let's think about, as in the context of an applied mathematician, I'm going to start actually shying away from HPC directly in the work that I've done most recently. However, I'm still thinking long-term about these tools, these algorithms and methods that could be used on these computers. So in 2008, I PI'd my first project. And remembering that we're applied mathematicians, we were motivated by something that we knew was coming down the line called the Energy Innovation Hubs. We knew that this nuclear modeling and simulation hub there was going to be a call for proposals, and that there was some algorithmic work that should be done. So the problem was really in light water reactors, or in nuclear reactors in general. So this class of problems, you know, from an applications point of view, has a lot of multi-physics and multi-domain problems. Now, it's not unique to light water reactors. It's actually across almost all applications DOE might be interested in, but this is the one we motivated our work with. So Castle has now come to fruition, and they're working on it. And what they're doing is they're taking existing codes that exist throughout the DOE, and they're trying to couple them together. And the challenge with doing that, is that when you do these coupling methods of just trying to couple two different softwares together, remember this software has been designed for a particular problem. It's probably the optimal method for that particular problem, and there's a lot of application knowledge embedded in that. But now they're trying to couple things together. Well, traditional coupling methods of this type of multi-domain, multi-physics problems generally lend themselves to two types of methods, Neumann-Neumann preconditioners or Morter methods. And these are good methods, but sometimes you can consider them to be ad hoc. Sometimes they're explicit, coupling across these domains, and they often encounter numerical accuracy and stability problems. So we wanted to do something a little more mathematically rigorous. So the challenge we identified was that often you have mismatched grids. So you're taking two computational domains. You could have mismatched grids. You could have mismatched discretizations. How do you get them to talk to each other in a mathematically rigorous way? So drawing on my optimization knowledge that I gained from Sandia and my PDE's knowledge that I gained in my PhD, I looked at this problem and said, can we pose this as an optimal control problem? So here's the toy problem. If you have a solid on one side, in one area of your domain, and a fluid in the other area of your domain, and you want to have continuity of some variable across this domain, how might you represent that? Well, I'm going to try and minimize, just like I did before, the cost functional. I'm going to call this variable that I'm trying to minimize. Think of it maybe as temperature, for example. I'm going to minimize the mismatch across that interface, and I'm going to constrain that by the governing physics and the boundary conditions in that domain. And I'm going to introduce a control variable, which in this case is going to be the derivative, or the flux across this interface. And so I'm going to control based on that flux, and this allows the application to use the optimal numerical method for each of those PDEs, which are going to be different for each of those domains. So here's an example problem. Solid, I'm going to have pure diffusion, like heat conduction, for example. I'm going to have convection up here, so this heat's going to be convecting off this, for example, hot plate, if you will. That heat convection is going to also affect the fluid flow, because I've got a fluid up here, so it's doing essentially a buoyancy type approximation here. I'm going to assume, for simplicity, that I have an incompressible fluid up here as well. Essentially, I've got a momentum equation, just like I've had in the past, a convection diffusion. Now, I introduced diffusion for a reason, and my standard incompressibility. I'm going to assume continuity of the temperature across this domain, as well as I'm going to assume the conservation of energy. So I'm going to balance the fluxes across that interface as well. Okay. So we have a couple of choices how to solve this. But the point is we did for this toy problem. So for a pure diffusion problem, so it's much simpler than what I just showed you, we demonstrated analytically that we could solve this problem using this optimal control approach. Everything matches, so here's your theta variable, your temperature variable that I showed you before, and there's your flux. Fine. Now, in this particular case, I had matching grids. So now I wanted to extend it. What if I have mismatching grids? So I'm really thinking towards the applications. I'm not solving the applications yet. Well, what we found is if you have mismatching discretizations, you encounter a little bit of a problem, and that's semi-convergence. So as I solve that optimization problem, I'm going to iterate through time. I'm going to look at the mismatch in the L2 norm at that point. So my first iteration, I'm up here around 0.5, and I decrease the mismatch, decrease it. I continue iterating. My solver doesn't tell me I'm converged. Now it starts increasing. That's a problem. I want to identify this particular, the well right here, and I want my simulation to stop here when I've done the best match that I possibly can. So with my graduate student, we looked at 3 different methods of doing this. We could decrease the resolution, so we could observe and control with piecewise constants. Well, I don't think my applications folks would be very interested because I'm going to jeopardize their accuracy at that boundary. Not really what I want to do. I could under-constrain if I wanted. There were some disadvantages with doing this. Instead, what we decided to do was employ some regularization. And this is where I'm going to hand wave and skip through it. And point out that as I refined my mesh using this implicit regularization that I'm not really giving you the details of, we found that we had this L curve that looked at the residual of the optimization problem that I was solving relative to the norm of the control function. And if we identified this red point right here, right at that L, it corresponded relatively well to the best solution that I could get. And these are analytical problems, by the way. This is not numerical hocus pocus. What's even better is as I resolve the mesh, so as the mesh gets finer and finer, and I identify that L curve, it gets closer and closer to the optimal solution with this extra regularization that I can get. So that seemed like a win. Now, this is not ready for prime time by any stretch of the imaginations. We've only done this on toy problems, but what we did do is we did demonstrate a robust method for coupling together different discretizations. What we found, though, is it's really a generalization that's a little bit more mathematically rigorous than Mortar methods. It is less efficient, so that's a concern. However, if you're doing a design optimization problem, you can add in this extra optimization problem for very little. And when I say very little, I mean very little extra cost. So depending on the type of problem that our applications folks want to solve, this would be potentially a solution for them. We demonstrated, we did the mathematical things and showed that we had the optimal rate of convergence. We got high accuracy, and we applied it to a few different problems of interest. So really, we want to continue on this. Before this is ready for production quality environment, we have lots of other problems that we still have to solve to be able to demonstrate this to our applications people. Okay. So that kind of brings us up to about a year ago. That project was from 2008 to 2009. So we've seen this increase in the top 500. It looks relatively linear. I did not mention, I don't think, that this is a log scale. I'm sure you all picked up on that. You can see that the slope of my computing experience actually has gone a little bit faster than the top 500, really as a result of this fellowship and the opportunities it's given to me. So what are we worried about next? We're worried about, obviously, from the talks yesterday, power and resiliency of these new machines. But from an applied mathematics point of view, what am I thinking about? I'm thinking about what new algorithms and numerical methods should we be using as we encounter these new architectures. Are these methods that I've just been talking about, are they going to scale to that next generation of an exascale? Even at a 20 petaflop machine, are they going to scale to that class of machine? However, if we have extra flops, this is also what's in the back of my mind. Can we start looking at improving accuracy using these extra flops that are going to be floating around for us, because we're no longer going to be flop limited, to improve the accuracy of our existing methods? So some of the things I'm working on more recently, how am I doing on time? 15 minutes? Oh, I got lots of time. I flew through this then. Including questions or? Oh, okay, then I'm right, okay, never mind. I'm not flying. So one of the things I'm working with is I'm working with an application called Home, which lives in the climate community. The climate community is an interesting community from a mathematics point of view. Now, I don't want to talk in detail about this, but Home is really cutting edge for the climate community. And what they've done is they've used spectral methods, which gives them high order accuracy and a high convergence rate, and coupled them with finite element methods, similar to what I've done in my past. But they've only done this in space so far. So I looked at Home, and I said, what about your temporal accuracy? What are you doing in time? Well, they're using a second-order leapfrog explicit method, which, to be fair, for their problems that they're interested in their applications at this moment in time, is more than adequate for them. But as the applied mathematician now, I'm starting to think longer term. What are they going to need once they solve some of their physics-based problems and their model-based problems? We need to be there and ready to support them when they start encountering new problems. So I started looking at the temporal discretizations. And so if you look at their benchmark problem, they have in the climate community, they have a suite of benchmark problems. And if you look at just their first shallow water benchmark problem, which everyone has to compare to, what this problem is they take essentially a Gaussian or a cosine bell, and they advect it around the globe. And they want to see that after 12 days, that the Gaussian shape is preserved. So essentially a conservation problem. And it is with their existing second order method. Being me, I said, well, what happens if I do this a little bit longer, like in a climate simulation? So if I continue advecting it around the globe for about 2.5 years, you can see that their temporal scheme, and I've made this an extremely fine spatial resolution so that I can try and take out as much of the spatial error as possible. You can see that their scheme is not really shape preserving at this point. And you can watch the error grow as a function of simulation time or number of simulation steps. So they're accumulating error. I said, well, some colleagues are experts in deferred correction methods. If we give them a different temporal discretization, if we give them just a fourth order deferred correction method, can we do better? And in fact, we can. Now, to be fair, you could probably put in a fourth order Runge-Kutta and see this exact same thing. But the advantage of this particular method is that I've shown here a fourth order method in these pictures here. But these deferred correction methods don't really have CFL time restrictions, time step restrictions. They allow for a much larger time step. Now, the advantage from my point of view is that now you're going to have a reduced number of time steps to get to your time to solution. So you can take much fewer time steps, thus accumulating much less temporal error. We also can give them an arbitrary order of accuracy. So while I've shown fourth order, we can also give them sixth order and eighth order. Now, if you look closely at this, this graph, here's a second order method, and that matches up with their existing second order method. You see the nice order 2 slope that you expect. If you see a fourth order method, you also see the fourth order slope that you expect. Now, when you start getting to sixth and eighth order, you start seeing this growth as you reduce the time step, and you don't expect that. And so lots of people look at this and go, well, your method doesn't work. Actually, I make a different argument because we can show this works on some other problems. This is where I'm encountering spatial error accumulation. I have now so well resolved the temporal problem for them that I'm now accumulating their spatial error. So I'm not, even though you're seeing a growth in error here, I'm not too worried about that from our point of view. Okay. So that's one thing I'm working on. But that, that is newer algorithms, but that, I'm not sure even that's going to scale to our Exascale. So what else am I working on? I'm also working on madness, which I do have to highlight that we won an R&D 100. It was recently announced in the last about a month or so we're pretty excited about that. I'm only going to briefly highlight on the computational kernels, but I'm pretty excited about this because I think this is one of the few codes that I've been involved with that has the opportunity to scale to much larger machines. Some of the things that it employs is it employs a discontinuous spectral kernel based on multi-wavelet basis functions. So I'm very familiar with spectral methods. The multi-wavelets have been new for me, but under the hood, really, they're a tensor product of coefficients. So lots and lots of small dense matrix multiplications. Madness has been designed specifically for fast computation. So it's multi-resolution. It's got a hierarchical basis functions. It also has low separation rank functions, so that also adds to the computational efficiency. But it's been designed to truncate based on user-specified precision. So this goes back to where I'm interested in accuracy, kind of ties into the homework as well. And all of this sits on top of a unique parallel runtime environment. This is not a small project. There are lots and lots of people involved. I'm one small piece of it. But what I found interesting as I was thinking about this talk is really the impact that this program has had on this particular piece of software in the last few years. So we've had 3 students come do their practicum with us. Matt Reuter came 2.5 years ago and worked on the implicit boundary conditions present in Madness. He's actually going to be joining Oak Ridge in about a month as a Wigner Fellow, so we're hoping we can get him back working on Madness some more. Paul Sutter came 2 years ago, the same summer that Matt came, and then actually came again for an HPC practicum and worked on the load balancing algorithms with Rebecca Hartman-Baker, some of which will be employed in Madness. Jeff Donatelli, who couldn't be with us this week, is currently doing his practicum at Oak Ridge with us, working on level set methods in Madness. And then Jeff Hammond has worked on, and Jeff can correct me if I'm wrong, worked on porting Madness to the Argonne BGP and is also involved with chemistry applications. So, even though this is just one project, CSGF has really helped us get some new methods that we haven't had the manpower to be involved, to have done yet. So, kind of in summary, what are some of the common threads that I hope you've gleaned from this? Well, one, I didn't start out looking to be a computational scientist or an applied mathematician, but now I'm constantly looking for applied math solutions to a problem, and I attribute that specifically to this program. I'm now much more aware that improved computational efficiency is important. I'm looking at algorithmic robustness. I look at scalability, and I look at accuracy. All of these are core computational science problems. But what I think is most unique about this particular program is that this program gave me the opportunity to learn many different languages. And so now I can work hand in hand with application specialists, appreciate what they do, and also help communicate what we can offer them as well. So this is the next to last slide. This is the last important slide. This is my advice to new fellows, or newer and younger fellows, the things that I wish I had known when I was sitting in your seat, because I was sitting in your seat about 10 years ago. And we've said this over and over and over all week. Network, 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 network. And that's like the pot calling the kettle black. I'm not very good at it, and I was terrible at it. But you have a unique opportunity to get to talk to people across disciplines in this program and learn their language and what they do. I know that it's tough right now, but that program of study is really your friend. Take advantage of taking these extra classes, or having the opportunity to take these extra classes and learn a language that your fellow graduate students in your discipline may not know, because it will serve you well in your career. Take advantage of the opportunity to broaden your experiences. Go to a practicum and do something different. As well as when you're at your practicum, talk to lab scientists, talk to other lab scientists. We love to talk about what we do. We can't shut up sometimes, as you all are probably thinking. And then really remember that this community that we're building, and I am so honored to be a part of it, is growing. And we are a resource. The alums are a resource to you. We are happy to help you. And there's also what I call these guardian angels. Some of them are sitting in the room who are also here to help you. So take advantage of that as well. I've put up a few of my collaborators. I am sure I've missed somebody. I've also want to acknowledge the sponsors. None of the work that I've talked about today, I should probably say this as well, computational science is not a single PI kind of problem. It is an interdisciplinary, large team problem. So I have lots of collaborators on all of these projects. Please don't think that I did any of this by myself. I also want to acknowledge the sponsors that have, I've talked about a lot of different work. So some of it's been funded by NSF, some by DOE, and some by internal LDRD. And I'd be happy to take any questions.